I'm Sunghyun from Postech. We present a system called iTurboGraph, which scales and automates incremental graph analytics. And this is a joint work with the authors from Postech and Hanyang University. Graph is an effective way to represent entities and their relationships. Examples are road, social, and web graphs. Using various analytics, valuable information can be discovered, such as shortest paths, communities, and ranks of pages. The real graphs are huge. Typical social scale graphs contain 100 billion edges, and web scale graphs have more than 1 trillion edges. Furthermore, the size of a brain graph, known as a human connectome, can reach 100 trillion edges. Another aspect is that these graphs even evolve over time. The network can grow over time and social relationship changes over time, and we call them dynamic graphs. However, most existing graph analytics systems focus on one-shot analytics, which repeatedly executes the same algorithm whenever the input graph is changed. Therefore, a small change incurs large computational costs for refreshing the analytics results. We exploit incremental graph computation technique. Here, we have as inputs graph G, query Q, and all the output Q of G, and changes on the graph delta G, such as edge insertions or deletions. The goal is to compute the changes delta O to Q of G, which can be used to refresh the analytics result without full recomputation. Next, I will explain the challenges in incremental graph analytics. The first challenge is scaling incremental computations for large graphs. Some existing systems need to maintain the intermediate result of the previous computations for incremental computations, which leads to their limited scalability. For example, for a graph with edges E, in PageRank, order of E messages are generated every super step. And in finding triangles, order of squared E intermediate results can be generated. The next challenge is to automate incrementalization of various graph algorithms. Commonly, users know only the one-shot algorithms, which assume the graph is static. Their incremental algorithms are not widely known and tend to be much more complex. That is, the manual approaches are error-prone and hard to reason about the correctness. Now I explain our contributions. We present a system called iTurboGraph, which is an end-to-end system consisting of its programming language, compiler, and runtime engine for incremental graph analytics. And we formalize graph streaming algebra as the intermediate representation of graph algorithms. Our compiler supports the automatic incrementalization of one-shot graph algorithms. It enables scalable processing by not maintaining the intermediate results for graph traversals and messages. This is an overview of our system consisting of a front-end query compiler and back-end distributed runtime engine. Users write a program Q with our programming language LNGA, then our compiler translates it into its algebraic representation GSA operations and automatically generates its incremental version, applying several optimizations. The distributed runtime engine processes one-shot query over the initial graph, or incremental query over the mutated graphs. The dynamic graph store maintains on disks the initial graph and graph mutations. We target supporting neighbor-centric graph analytics, NGA for short. Vertex-centric model is widely used where a user expresses the computations over one home neighbors around each vertex. However, there are important types of analysis algorithms called neighbor-centric graph analytics in NGA as a generalization of the vertex-centric one. Users can traverse over multi-home neighbors around the vertices and perform computations, and examples include triangle counting and pair matching. To implement NGA on vertex-centric systems, users need to construct a multi-home neighborhood by themselves around each vertex by exchanging the messages containing the list of neighbors, and which is not intuitive for programming NGA. Next, I will motivate our programming language NGA with triangle counting as an example. The left figure shows its implementation in a vertex-centric model using message passing. Let me explain how it finds a triangle of vertices 1, 2, 3 on the graph at the right side. First, vertex 1 sends a message with its vertex ID to a vertex 2, its neighbor, and vertex 2 appends its vertex ID to the message and sends it to vertex 3. Then, vertex 3 checks the first vertex ID in the received message, which is its 2 home neighbor, is also its 1 home neighbor. If it is, it increments the counter value by 1. As you see, in a vertex-centric model, programming NGA is not intuitive. Here, traverse function shows much more intuitive implementation of this triangle counting query using nested for loops. It performs graph traversals from a vertex U1 to U2, and U2 to U3, and U3 to U4. If U1 is equal to U4, then we find the triangle and we increment the counter value by 1. And this LNGA is a domain-specific language for neighbor-centric graph analytics. A user can easily express the graph traversals within multi-home neighborhoods around each vertex using nested for loops. Our compiler parses the one-shot algorithm written in LNGA into its intermediate representation and automatically generates its incremental algorithm. Now I explain graph streaming algebra. We call it GSA. GSA is a formalization of nested windowed streaming model, which is designed for scalable streaming graph processing. And it is an intermediate representation of NGA algorithms. And after expressing the one-shot algorithm in GSA, our compiler applies incrementalization rules to derive an incremental algorithm. We model the graph data as streams. Vertex stream is a sequence of vertex tuples, and edge stream is a sequence of edge tuples, and graph stream is a pair of vertex and edge streams. In the below figures, Figure A shows an example graph G0, and Figure B shows vertex stream VS and edge stream ES. And in this example, vertex stream is a tuple of a vertex ID and its degree, the number of neighbors. And edge stream is a tuple of edge tuples, which is a pair of source and destination vertex IDs. We modeled graph traversals as enumeration of walks. We define a walk of a length k as a sequence of k plus 1 connected vertices. With the below graph G0, I explain the walks of lengths 1 and 2 starting from vertex 1. For the length 1 walks, it corresponds to the direct edges from vertex 1 to vertex 0 and vertex 5. For the length 2 walks, we go one hop further from the ending vertices of the length 1 walks, that is vertex 0 and 5, like this. These walks represent the graph traversals. Next, I explain the streaming operators in GSA. For graph traversals, we define a walk generation operator omega, and it corresponds to join in relational algebra. A walk generation operator takes as inputs k graph streams and outputs a stream of walks of length k. In addition, we adopt several standard streaming operators such as filter, map, and accumulate, and I will omit their explanation. LNG program is compiled into GSA query plans, and the below figures show the traverse function of PageRank and its expression tree. First, each LNJ statement is translated to the corresponding GSA expression. Then the translated expressions are merged into a single expression, like this expression tree, and we use the apply operator. And this apply operator is widely used to model correlated subqueries. And please refer to our paper for detailed explanations such as its decorrelation. I explain how to support incremental graph analytics. A one-shot query queue performs iterative superset computations over the initial graph G0 until the attribute values such as PageRank values converge. Like this. It starts from the initial superstep and it goes on until it converges. Now, given the graph mutation delta G1 and the changes against the previous attribute values, an incremental query delta Q refines the previous results starting from the first superstep until no changes is discovered. Here, the incremental computations are performed only when the final results can possibly change. Then we explain our data model. The issue is how to represent graph mutations and attribute value updates. In our model, a tuple has either +1 or -1 multiplicity. +1 represents an insertion of the tuple, and -1 represents a deletion of the tuple. And we call the stream representing updates or changes as a delta stream, delta S. And for graph mutation, insertion or deletion of an edge with multiplicity +1 or -1. And for attribute value update, we model it as deletion and insertion. That is, deletion of the tuple with the previous value and insertion of the tuple with the new value. Then, how do we generate incremental algorithm of a user program? After translating the LNG program to GSA plans, we apply the incrementalization rules for individual GSA operators, and the rules are shown here in figure 1. The important point is that GSA is closed under incrementalization, that is, for the program of GSA, its incremental program also consists of GSA. Therefore, both one-shot and incremental queries can be processed by the same execution engine, which supports GSA. Figure 2 shows the difference between Q and DQ, and delta Q additionally takes as input the delta graph streams for the graph mutations and changes in attribute values. Another important part for incrementalization is to support for the accumulators, that is value aggregation. We support incremental value aggregation over abelian monoid or group. Abelian monoid has a commutative and associative operation f, and examples are min and max. An abelian group additionally has an inverse function, and examples are sum and product. For abelian group, we can easily support the deletions by using the inverse. For example, when we found some removed triangles, we simply decrement the counter value. For abelian monoid, we may perform recomputations of the accumulator under deletions. And for further details with possible optimizations, please refer to our paper. I will explain our experimental setup. We use 3 groups of queries, and group 1 consists of iterative matrix vector multiplication algorithms such as PageRank and label propagation. And group 2 solves connectivity problems such as connected components and BFS. And group 3 are representative neighbor-centric graph analytics algorithms such as triangle counting and local clustering coefficient. And we generate the workloads as follows. We use both real and synthetic graphs, and for the initial graph, we use the 90% of sampled edges from the input graph. And for the updates graph mutations, we use a batch of 100k updates with 75k insertions and 25k deletions. Here is our competitors. Differential data flow is a distributed and in-memory system based on a relational model. It provides automatic query incrementalization of its data flow program. However, as it is an in-memory system and has to keep the intermediate results for incremental computations, its scalability is limited. And in this talk, we only present the results against differential data flow. We first show the overall performance for each group against differential data flow. This strategy of maintaining the intermediate results might be reasonable for some workloads with small intermediate result sizes. However, graph algorithms typically generate a lot of intermediate results. For both queries, DD shows its limited scalability incurring disk swaps or auto memory errors. Now, iTurboGraph does not keep the intermediate results and scale to large graphs. These are for group 2 queries, and we observe the similar trends, but note that for BFS, DD's incremental computation is slightly faster than iTurboGraph. This is because BFS generates small intermediate results. Now we show the group 3 results. Multi-op graph traversals involve self-joins of edge tables, and it generates significantly large amount of intermediate results. Therefore, only iTurboGraph can process up to the largest graphs. And we also test the scalability. For PageRank and triangle counting queries, we measure the execution times varying the size of the graphs. And DD incurs disk swaps at some points and crashes with the auto memory errors, but iTurboGraph scales to the largest graph efficiently. Now we conclude. iTurboGraph achieves automatic incrementalization of neighbor-centric graph analytics and scalable processing of incremental computations. With our proposed graph streaming algebra, and a compiler for automatic query incrementalization, and incremental NGA without maintaining the intermediate results for graph traversals and messages. Okay, thank you for listening my presentation.